Hello, in this video we'll be working on Unit 7 homework problems 1 through 12. Number 1, the function f is differentiable for all real numbers. The point 3, 1/4 is on the graph of y equals f of x, and the slope at each point x, y on the graph is given by dy dx equals y squared times 6 minus 2x. Part A asks us to find the second derivative, d squared y over dx squared, and evaluate it at the point 3, 1/4. So we already have an equation for our first derivative. We know that dy dx equals y squared times 6 minus 2x. The second derivative is just going to be the derivative of this. So on the left-hand side, we're taking the derivative of dy dx, and that gives us the d squared y over dx squared. On the right, we're going to use product rule, and we have to use implicit differentiation here since we have variables x and y. We're taking the derivative with respect to x. So when we get to the part where we take the derivative of y, chain rule kicks in, we multiply by dy dx. So product rule, we start by taking the derivative of the first, that's 2 times y times dy dx. Then we multiply by the second factor, plus the first factor times the derivative of the second. The derivative of the second is just -2. So that is our second derivative, and we want to evaluate that at 3, 1/4. So we let x equal 3, we let y equal 1/4. So we need 2 times y times dy dx, and so in order to figure out the value of dy dx, I have to sub in my coordinates into my dy dx equation. So let's go back up here. Dy dx at 3, 1/4 equals y squared, so 1/4 squared, times 6 minus 2 times 3. 2 times 3 is 6, 6 minus 6 is 0, 0 times 1 over 16 is 0. So the derivative at this point is 0. So let's go back here. We're evaluating the second derivative. So I have 2 times the y coordinate times dy dx, which is 0, times 6 minus 2x, doesn't even matter what that is because this whole factor is just going to be, or this whole term is just going to be 0. But 6 minus 2 times 3, if I want to be thorough, oh, and there we have 0 again. So that whole thing right there is 0, plus y squared, so 1/4 squared is 1 over 16, times -2, which gives me, in the end, just -1 over 8. Part B, find y equals f of x by solving the differential equation dy dx equals y squared times 6 minus 2x with the initial condition f of 3 equals 1/4. So let's write down our differential equation. We've got dy dx equals y squared times 6 minus 2x. The first thing I want to do is to separate my variables. So I'm going to multiply both sides by dx. And I'm going to divide both sides by y squared, or multiply both sides by 1 over y squared. Now I've got a function in terms of y times dy equals a function in terms of x times dx, so I can integrate both sides. Let me rewrite this. So I have 1 over y squared dy equals 6 minus 2x times dx. So something times dy plus, or equals, something times dx, so now I'm going to integrate both sides. The integral for 1 over y squared dy is -1 over y. The plus c I'll save for the other side. And then on the right, I've got the integral of 6 minus 2x times dx. So that's going to be 6x minus x squared plus c. This is my general solution. Now, if I want to solve for y, I have a couple options. I think the easiest is going to be, so we could cross multiply, that's a possibility, but I think the easiest thing is going to be to multiply both sides by -1 and then take the reciprocal of both sides. So let me go ahead and do it in 2 steps. First, I'm multiplying both sides by -1. So I have 1 over y equals, my 6x is going to become negative, my x squared is going to become positive. So I have x squared minus 6x. And then when I multiply c by -1, I get minus c, but minus c really is just a constant. It's just a placeholder for a constant. So whether I write plus c or minus c, it's still a generic constant for the time being. But this c now, if I were to solve for c in this line, I'd get a different result than if I were to solve for c in the line above. So I need to distinguish them. I'm just going to put a little subscript on my old one. And now I'm going to take the reciprocal of both sides so that I have this function solved for y. So the reciprocal on the left is just y. The reciprocal on the right is 1 over x squared minus 6x plus c. So this is my general solution. We're asked to go one step further and find the particular solution given that our initial condition is f of 3 equals 1/4. So y equals 1/4 when x equals 3. That gives me 1 over, so x is 3, so x squared would be 9, minus 6 times 3, so minus 18, plus c. And now I have two fractions equal to each other. The numerators are the same. That means the denominators must be the same. Otherwise, these fractions wouldn't be equal. So now I can simply solve 4 equals 9 minus 18 plus c. 9 minus 18 is -9 plus c. And then if I add 9 to both sides, I get c equals 13. So I'm going to come back up here to my general solution, and I'm going to substitute 13 in for c. And that's going to give me my particular solution. So my final answer would be y equals 1 over x squared minus 6x plus 13. Number 2, consider the differential equation dy dx equals 3 minus x over y. Part A, let y equal f of x be the particular solution to the given differential equation for x between 1 and 5, such that the line y equals -2 is tangent to the graph of f. Find the x-coordinate of the point of tangency and determine whether f has a local maximum, local minimum, or neither at this point. So first of all, notice that y equals -2 is a horizontal line. That means we have a horizontal tangent, and a horizontal tangent has a slope of 0. So we know that at this point in question, this point of tangency, dy dx is equal to 0. And dy dx is a fraction, right? We have dy dx equals 3 minus x over y. And we know that's equal to 0, and that is only going to be equal to 0 when the numerator is 0. So from there, we can conclude that 3 minus x is 0, which means that x is equal to 3. So our point of tangency is 3 comma -2. Now we want to know if our function has a local max, local min, or neither at this point. We know that the first derivative at this point is 0. So let's do a second derivative test rather than, if we do a first derivative test, we need a sign chart, and then to test our derivative, we need the equation for y, which we don't have. We can get if we solve our differential equation, and that may be what was intended in this problem. But I think it's going to be easier if we do a second derivative test. So for that, we need to find our second derivative. So on the derivative of the left, the derivative of dy dx is d squared y over dx squared. On the right, I'm going to use the quotient rule. So I take the derivative of the top, which is -1, times the bottom, minus the top, times the derivative of the bottom, and the derivative of y is dy dx, over bottom squared. And now I'm going to evaluate this second derivative at this point of tangency. So second derivative at 3 -2 equals -2 minus 3 minus 3 dy dx. That's convenient, so I don't really need to find dy dx. Well, I know dy dx is 0 anyway at this point, over y squared. Okay, so this term is 0, and I just end up with 2 over 4, which is 1/2, and the important thing is not that it's equal to 1/2, but that it's positive. Since it's positive, I know that our original graph, y equals f of x, is concave up at this point, and the first derivative is 0, so it has a horizontal tangent. It's concave up at this point, and it has a horizontal tangent, so it must be a relative minimum by the second derivative test. So f has a local minimum at this point, 3, negative 2, since f prime of 3 equals 0 and f double prime of 3 is positive. Part B, let y equal g of x be the particular solution to the given differential equation on the interval from -2 to 8 with the initial condition g of 6 equals -4. Find y equals g of x. So now we're going to solve our differential equation. So I'll recopy it. We've got dy dx equals 3 minus x over y. I'm going to separate my variables, so we multiply both sides by y and multiply both sides by dx. Now I have something times dy equals something times dx, so I'm going to integrate both sides. On the left, the integral of y dy is y squared over 2 plus c, but I'll save my c for the other side. And then I integrate the right-hand side. I get 3x minus x squared over 2 plus c. So that's my combined constant term. Now I can solve for c and then solve for y, or I can solve for y first and then solve for c, whichever you like. We are asked to find y equals g of x, so we do have to solve it for y. In this case, I don't think the algebra is going to be too bad. Let me go ahead and multiply everything by 2, and then maybe we'll solve for c at that point. So if I multiply all the terms by 2, I get y squared equals 6x minus x squared plus 2 times c. Now 2 times c is still a constant. If you take the number 2 and you multiply it by a constant, you still get a constant. You don't get the same constant. You get a constant that's twice as big as the old constant, but it is still a constant. So I'm going to call it plus c, and then I have to call the old constant something different. So I'll call the old one c1. Now I'm going to solve for my constant here. So I have my initial condition, g of 6 equals -4. So -4 squared, I'll just come over here. -4 squared is 16 equals 6 times 6 minus 6 squared plus c. So I get c equals 16. And then I'm going to substitute that back in to my general solution. So I get y squared equals 6x minus x squared plus 16. If we had solved for c over here in this equation, we would have gotten c equals 8, and then when we multiplied through by 2, in the end, we would have the same result, where we have 6x minus x squared plus 16. So you can solve for c at any point in this process, and you should still end up with the correct answer. We do need to continue to solve this for y. In order to do that, I'm going to take the square root of both sides. The square root of y squared could be positive y, it could be negative y. So we have to consider our initial condition. Y equals plus or minus, I have to figure out whether it's going to be plus or minus, the square root of 6x minus x squared plus 16. And I know that when x is 6, y is negative 4. The square root can only produce non-negative values. So the only way this can equal negative 4, the only way y can equal negative 4 is if I have a negative sign in front of my square root. So I know it's not positive. It's only the negative. And that makes this my final solution. Number 3, oil is being pumped continuously from a certain well at a rate proportional to the amount of oil left in the well. In other words, dy dt equals k times y. When you see proportional to, we know that we're multiplying by a constant. In this case, we're calling that constant k. So we have a differential equation, dy dt equals ky. Y is the amount of oil left in the well at any time t. Initially, there are 1 million gallons of oil in the well, and 6 years later, there are 500,000 gallons remaining. It'll no longer be profitable to pump oil when there are fewer than 50,000 gallons remaining. So part A wants us to write an equation for y, the amount of oil remaining in the well at any time t. We know the equation for the derivative of y with respect to t. dy dt equals k times y. And we want to come up with an equation in the form of y equals. So we have to solve this differential equation. We're going to separate variables, get all the y's and dy's on the left, and all the t's and dt's on the right. So let's multiply both sides by dt, and then divide both sides by y. That gives 1 over y dy equals k times dt. K is a constant, not a variable. So I have separated my variables. I've got the y stuff on the left, the t stuff on the right. Now I'm going to integrate both sides. The integral of 1 over y dy is natural log absolute value y plus c, but I'm going to save the plus c for the other side. On the right, the integral of k dt, this is just a constant. When you integrate a constant, you get that same constant times your variable. We're integrating with respect to t, so it'd be kt plus our constant c. This is my general solution, although it has not yet been solved for y. And if you look at the instructions, it says write an equation for y. So now we have to solve this for y. It doesn't specifically say to find the particular solution, but we have enough information to do so. So let's go ahead and solve for c. We can do that now, or we can wait. I think I'm going to wait and solve for y first, and then I'll go ahead and solve for c. So the next thing I'm going to do is exponentiate both sides. That means I'm going to take the left-hand side. I'm going to do e raised to the left-hand side equals e raised to the right-hand side. And then I can simplify. E to the ln absolute value y is just absolute value y equals e to the kt plus c. To drop the absolute value, I put a plus or minus in front. And then I'm going to multiply both sides by plus or minus. So the plus or minus essentially gets moved to the other side. E to the kt plus c. Now I'm going to separate e to the kt plus c into e to the kt times e to the c. And e to the c is just a constant term. E is a constant, c is a placeholder for a generic constant, and so when you have a constant raised to the power of another constant, you just get a constant. So all of this becomes just a constant. I'm going to call it c. When we multiply by a constant, we normally write that in front of the term. So now I have y equals plus or minus c e to the kt. So this c that I just wrote is not the same as the c from the last step. So I need to call the old c something different. Now plus or minus c is still just a constant term. Plus or minus c is really still just c. It's not the same c, it's a different c, but it can be represented with a single letter constant. So I'm going to use c for constant, and then I have to call the old c something different. So now I just have CE to the KT. That is my general solution right here, general solution. To find the particular solution, we have to sub in some initial condition. And we were told that there were 1 million gallons of oil in the well initially, so at time 0. So now I can say when y is 1 million, t is 0, k times 0 is 0, e to the power 0 is 1, so this just becomes 1, and c is a million. So my particular solution is y equals 1 million e to the kt. Now we still have this constant k in our equation. We want to solve for k. And we were given a second point, and that will help us solve for k. We were told that 6 years later, the amount was 500,000. So we'll sub that in, 500,000 equals 1 million e to the k times 6. So e to the 6k. And then we're going to solve that. So 500,000 divided by 1 million is 1/2. So get 1/2 equals e to the 6k. And then we can take the natural log of both sides. Natural log of 1/2 equals natural log of e to the 6k. The natural log of e to the 6k is just 6k. And then if I divide by 6, I get k equals the natural log of 1/2 divided by 6. Which is negative 0.1155. So now we can go back to our solution and sub that value in for k. So in the end, my final equation is y equals 1 million e to the negative 0.1155 t. Part B, at what rate is the amount of oil in the well decreasing when there are 600,000 gallons of oil remaining? So we need to figure out when that is the case. So we're solving for t. We want to know at what time t is the amount equal to 600,000. So we'll let y equal 600,000 and solve for t. 600,000 equals 1 million e to the negative 0.1155 t. So we can solve this for t and then use that value of t to evaluate the derivative. We have the derivative dy dt equals ky. And now that I'm looking at the derivative, okay, we have dy dt equals k times y. There is no t in our derivative, so solving for t here is actually not necessary. It's not going to help us. All we need to know in order to find the derivative at time t is our k value, which we've already found. So we know that this is actually negative 0.1155y. That's what our derivative equation is now. All we really need to know is a y value, and we can find our derivative at time t. And in this case, our y value is 600,000. So dy dt, when y equals 600,000, equals negative 0.1155 times 600,000. And that is equal to negative 69,300. The units here are going to be gallons per year. So our units of time were years, and units for gallons, or units for the amount of oil were gallons. So gallons per year. And part C, in order not to lose money, At what time t should oil no longer be pumped from the well? Well, we were told at the end of the problem it'll no longer be profitable to pump oil when there are fewer than 50,000 gallons remaining. So we have an equation for the amount of oil. That's our 1 million. E to the negative 0.1155 T. That's the amount of oil. We want to know, when is that going to be less than 50,000? So we're going to solve this one on the calculator, but to save me from having to use a really large viewing window, let's simplify a little bit. If I multiply both, or if I divide both sides by 1 million, I get e to the negative 0.115 t is less than 50,000 over 1 million. Okay, so right away I can do that, and then 5 over 100 is 1 over 20. So e to the negative 0.115 t, when is that less than 1 over 20? Okay, so I'm going to enter e to the power negative 0.1155 times t, and then 0.05 in y2. Let's try zoom 4, see if that works for us. Not quite, we need to go out farther. So x min, make that 0, x max, let's just try 20. That might do it. Let me fix my window even more. So really, I'm going to look between negative 1 and 1, and then I'm going to go farther to the right. Nope, that's not what I meant to do. Y is between negative 1 and 1. And my x's will go 0 to 25. Did I just do 0 to 20? Let's make it 0 to 30. Let's see how that does. All right, I think I've got a point of intersection there. So let's do second calc. Intersect, enter, 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 and I get 25.937. Now e to the negative 0.1155 t, that's the blue curve. So that is greater than 0.05 until I hit this point of intersection, and then it's less than 0.05 after I pass through that point of intersection. So my solution is going to be t greater than this value, t greater than 25.937. And the units there are years. Number 4, let P of t represent the number of wolves in a population at time t years, where t is greater than or equal to 0. The population P of t is increasing at a rate directly proportional to 800 minus p, where the constant of proportionality is k. So first, if P of 0 equals 500, find P of t in terms of t and k. We need to translate the information given to us into an equation. So let's read it one more time. P of t represents the number of wolves, and it's going to be difficult if we stick with that function notation, so we're just going to say P represents the number of wolves. The population P is increasing at a rate. When it says at a rate, it's talking about a derivative, the derivative of P with respect to time t. So that's dp dt. dp dt is the rate at which P is increasing. So it's increasing at a rate directly proportional to. When you see directly proportional to, it means you're multiplying something by a constant. What are you multiplying by a constant? Whatever it says it's proportional to. It's proportional to 800 minus p in this case. So it's increasing at a rate. So the rate is directly proportional to 800 minus p. And we have to multiply. It tells us the constant of proportionality is called k. So it's k times 800 minus p. There's our differential equation. We want to find p of t in terms of t and k. So we don't have to solve for k, at least not yet. In part B, it's going to ask us to solve for k. To solve this differential equation, we want to separate variables. We need p stuff on one side, t stuff on the other side. So I'm going to multiply both sides by dt. I'm going to divide both sides by 800 minus p. So that gives me 1 over 800 minus p dp equals k times dt. K is a constant, not a variable, so it can stay with the t stuff. Now I'm going to integrate both sides. When I integrate 1 over 800 minus p, I need to use U-Substitution. So if I work out all the U-Substitution, and this is one that I could do in my head, knowing that if I let u equal 800 minus p, the derivative of u is just going to be -1. The derivative of u with respect to p is just going to be -1. And so to compensate, then I know that means that dp is just going to equal -1 times du. So it's going to become 1 over u, the integral 1 over u times -1 times du. So that integrates to the natural log of the absolute value of 800 minus p times -1 plus c, but we'll save the c for the other side. On the right, when I integrate k times dt, I get kt plus our constant c. So now we want to find p. We have to solve for p. It's asking us in this problem to solve for p of t. So we have to isolate the p. We've got a lot of stuff to get rid of. We have to get rid of the 800, the negative in front of the p, the absolute value, the ln, and the negative out in front. So let's deal with the negative out in front first. This is going to be ln absolute value 800 minus p equals negative kt minus c. The minus c, I can write minus c, or I can write plus c. Since minus c is just a constant term, we can call it plus c as long as we differentiate it from the old c. But I'm just going to leave it like this for now. Then I'm going to exponentiate both sides. So I get e to the ln absolute value 800 minus p equals e to the negative kt times e to the negative c. So I split up e to the negative kt minus c using my exponent rule for adding exponents. And here I am going to simplify this. E to the negative c is a constant raised to a constant power. That's just another constant. It's just a new constant. So I like calling my constant c, but in order to call this new constant c, I have to call the old constant something else. So I'll go back and just call that c1. So now I have, and then over here, the e's and the ln cancels out. So I have the absolute value of 800 minus p equals c, my new constant, times e to the negative kt. I'm going to drop my absolute value, and when I do that, I have to multiply by plus or minus 1. And I can do that here on the left, and then multiply both sides by plus or minus 1. It's essentially just going to move the plus or minus to the other side. So then I have plus or minus ce to the negative kt. And now here, plus or minus c is still a constant term. So I like to call my constant term c. So I'm going to call that constant term c. But now it's a different c than it used to be. So I have to call the old c something else. So just put a new subscript on the old c. And I'll keep going. So now I'm going to subtract 800. So that gives me negative p equals negative 800 plus ce to the negative kt. And then finally, multiply both sides by -1, I get p equals 800 minus ce to the negative kt. And here, if I wanted to, I could call that plus c. I'm just going to leave it like so. In part A, we were asked to find p of t in terms of t and k. So we do have to solve for c. And we were told that p of 0 equals 500. So when t is 0, p is 500. So 500 equals 800 minus ce to the 0. We're letting t equal 0. So e to the 0 is 1. 800 minus 300 is 500. So here c is 300. So my solution is going to be p equals, if I want to switch back to function notation now I can, p of t equals 800 minus 300 e to the negative kt. And then in part B, we're given another point on the function p, and that's going to allow us to solve for k. So I know p of t equals 800 minus 300 e to the negative kt. P of 2 equals 700. So now 700 equals 800 minus 300 e to the negative 2k. And we want to solve for k. So I can subtract 800 on both sides. That'll give me negative 100 equals negative 300 e to the negative 2k. I can divide both sides by negative 300, so I get 1/3 equals e to the negative 2k. Then I can take the natural log of both sides, and I get the natural log of 1/3 equals negative 2k, and then divide by negative 2, so k equals the natural log of 1/3 divided by negative 2. So let's simplify that. ln of 1/3 divided by negative 2 gives me 0.549. So k is approximately 0.549. Now we can put that value of k into our equation. So we have p of t equals 800 minus 300 e to the negative 0.549 t. And in part C, we're asked to find the limit of p as t approaches 0. Limit of p of t as t approaches, not 0, I don't know why I said that, as t approaches infinity. As t approaches infinity. So I think it'll be helpful if we don't have this negative exponent here. So let's write that as 800 minus 300 over e to the positive 0.549t, and I'm taking the limit as t approaches infinity. So I have e raised to an infinitely large power, which is going to approach infinity. So I have 300 over infinity. Okay, so 800 minus 300 over infinity. 300 over infinity, that's like 300 over a billion, way, way, way more than a billion. But if you were to say that number out loud, it's like 300 billionths. It's a really, really tiny number. It's approaching 0. So then the limit is just 800 minus 0, or 800. Number 5, a yam is put into a 200 degrees Celsius oven and heats up according to the differential equation dH dt equals negative k times h minus 200, with k as a positive constant. If the yam is at 20 degrees Celsius when it's put into the oven, solve the differential equation. So let me write down the differential equation first. We have dH dt equals negative k times h minus 200. We want to separate our variables, put all the h stuff on the left, put all the t stuff on the right. So I'll divide both sides by h minus 200 and multiply both sides by dt. So 1 over h minus 200 equals negative k dt. Now that we've separated variables, we can integrate both sides. On the left, the integral, oh, I dropped my dh, there we go. The integral 1 over h minus 200 dh is natural log of the absolute value of h minus 200. Technically, we need to use a U-substitution here, but the derivative of h minus 200 is just 1, so it becomes 1 over u du, which integrates to ln absolute value u, plus c, but we save our c for the other side. And then on the right, the integral of negative k dt is negative kt plus our constant c. So we have a general solution. We want to take this farther. We're going to solve it for h, and we also need to solve for c. First thing I'm going to do is exponentiate both sides. So e to the ln h minus 200 absolute value is just absolute value of h minus 200. On the right, I exponentiate. I get e to the negative kt plus c, and we saw this in the previous problem. Adding a plus c in the exponent, I can split this up and make it times e to the c, which just becomes a new constant. So that's going to be c e to the negative kt. And then when I drop my absolute value, h minus 200, I get a plus or minus on the right-hand side, but that gets absorbed into my constant term as well. So I have h minus 200 equals c e to the negative kt. And then I would add 200. So my general solution, h equals 200 plus c e to the negative kt. We're going to solve for c by substituting in values for t and h. We know that the yam is at 20 degrees Celsius when it's put into the oven, so we're going to assume that when it's put into the oven, we're at time t equals 0, and the temperature there is 20. So 20 equals 200 plus c e to the 0. E to the 0 is 1. So then we have 20 minus 200, or negative 180, equals c. So my equation becomes h equals 200 minus 180 e to the negative kt. Part B used the fact that after 30 minutes the temperature is 120 degrees Celsius to find k. Now we need to make another assumption here. We weren't told specifically what the units were for t. So if we let t be minutes, then we're subbing in 30 for t and 120 for the temperature h. If t is in hours, then 30 minutes would actually be half an hour, so t would be 1/2. But let's go ahead and use minutes for our units on t. So we get 120 equals 200 minus 180 e to the negative 30k. We'll do 120 minus 200, so that's negative 80, and then divide by negative 180 equals e to the negative 30k. So 80 divided by 180. Then we're going to take the natural log of both sides, and we're going to divide by negative 30. And we get k equals 0.027. We weren't asked to go further. We could now go back to our general solution or our particular solution and sub in 0.027 for k, but part B is just asking us to find k, so we'll stick with that. Number 6, a detective finds a murder victim at 9 a.m. The temperature of the body is measured at 90.3 degrees Fahrenheit. 1 hour later, the temperature of the body is 89 degrees Fahrenheit. The temperature of the room has been maintained at a constant 68 degrees Fahrenheit. Newton's law of cooling states that the rate of heat loss of a body is proportional to the difference in temperatures between the body and its surroundings. In other words, dt over dt, d temperature over d time, equals negative k times T minus Ts, the difference between the temperature and the surrounding temperature. And the solution to this differential equation is given by T, temperature, equals Ts, the surrounding temperature, plus T sub 0 minus Ts times e to the negative kt, where T sub 0 represents the initial temperature. So assuming that the temperature T of the body obeys Newton's law of cooling, write a differential equation for T. Okay, so we can use this as a guide. Our differential equation is going to be d temperature over d time, dt over dt, equals negative k times, and then we have T minus T sub s. So T is the temperature at time t, minus the surrounding temperature, that would be the room temperature. It tells us that the room has been maintained at 68 degrees Fahrenheit, so T minus 68. Part B wants us to solve this differential equation to estimate the time the murder occurred. So we're trying to solve for little t. We're going to start by separating variables. Unfortunately, both of our variables are called t. We've got big T, we've got little t. So I want all the big t's on one side, I want all the little t's on the other side. I'm going to divide by T minus 68, and I'm going to multiply by dt. So then I get 1 over T minus 68 equals negative k dt. And, oh, I dropped my dt. Okay, and then we integrate both sides, and we get natural log absolute value T minus 68. We'll save our plus c for the other side, equals negative kt plus c. We're going to exponentiate both sides, and then our e to the c is going to become our new constant multiplied out in front. So it's going to work just like the previous couple problems we looked at. We have T minus 68 equals a new constant c, e to the negative kt. And then this is a different c, so I'll call the old c something else. So T, temperature, equals 68 plus CE to the negative KT. We're going to use the other information we have to try and solve for some of these unknown values. So we know the temperature of the body is measured at 90.3 at 9 a.m. and then an hour later, the temperature is 89 degrees Fahrenheit. So we'll just say when the body was found, we'll call that time T equals 0. So our temperature is 90.3 at time 0. So that's going to be our reference point, our starting point, plus C e to the 0, which is just 1. And that gives us a C value of 22.3. So now we know T minus 68 equals, or let me use the, let's use this one instead. So T equals 68 plus 22.3 e to the negative kt. 1 hour later, so here we'll assume our units for T will be hours. 1 hour later, so when T is 1, we have the temperature as 89. So now we have 89 equals 68 plus 22.3 e to the negative k times 1. So we'll do 89 minus 68. Divide that by 22.3. Take the natural log and then divide by 1. That gives us k equals 0.0601. So now we have our particular solution, T equals 68 plus 22.3 e to the negative 0.0601 T. We can use this to find the temperature at any time little t. Now, assuming that a person's normal body temperature is 98.6, we can figure out what time it was when the temperature was 98.6. So we'll do 98.6 equals 68 plus 22.3 e to the negative 0.0601 t and solve for t. So we subtract 68, divide by 22.3, take the natural log of the left-hand side, and then divide by negative 0.0601. And we get t equals negative 5.265. And t is measured in hours, and when t is 0, it was 9 a.m. So we have to go back 5.265 hours from 9 a.m. So if we go back 5 hours, we're at 4 a.m., and then we have to go back even more. We have to go back another 0.265 hours. Remember, an hour is 60 minutes, not 100 minutes. So if we multiply 0.265, let me grab the calculator. If we multiply 0.265 times 60 minutes, we get 15.9 minutes. So let's just say 16 minutes. Okay, so from 4 a.m. we have to go back another 16 minutes. So that's approximately 3:44 a.m. Number 7, use separation of variables to solve the initial value problem. dy dx equals cosine x over 3y squared, where y of pi equals 5. So we have dy dx equals cosine x over 3y squared. To separate variables, we multiply both sides by 3y squared, multiply both sides by dx. So we have 3y squared dy equals cosine x dx. Then we can integrate both sides. So on the left, we get 3y cubed over 3, or just y cubed, plus c, but we'll save that for the other side. On the right, the derivative of sine x is cosine x. So we have sine x plus c. We can solve for c now, or we can solve for c after we solve for y. Let's go ahead and solve for c now. So y of pi equals 5. So we have 5 cubed, which is 125, equals the sine of pi plus c. The sine of pi is 0, so that means c equals 125. So we can go back to our equation, y cubed equals sine x plus 125. And to solve for y, I just need to take the cube root of both sides. So I get cube root of sine x plus 125. Number 9, the change in n, the number of bacteria in a culture dish at time t, is given by dn over dt equals 2n. So dn dt equals 2n. If n equals 3 when t equals 0, find the approximate value of t when n equals 1210. Let's separate our variables and solve our differential equation. So multiply both sides by dt, divide both sides by, you can either divide both sides by 2n, or you can leave the 2 on the right and just divide both sides by n. That's what I would prefer to do, because if I divide both sides by 2n, it's going to put the 2 in the denominator on the left-hand side, and it's just easier to work with 2 than it is to work with 1/2. So I'm going to leave the 2 on the right. I'm going to divide by n, so I get 1 over n dn equals, I left the 2 over here, I multiply by dt, so I have 1 over n dn equals 2 dt, and now I'm going to integrate both sides. So the derivative of 1 over n dn, or I'm sorry, the integral of 1 over n dn is ln absolute value n, and we'll save the plus c for the other side. On the right, our integral of 2 dt is 2t plus c. Now we exponentiate both sides, and e to the 2t plus c, we can make e to the 2t times e to the c. So I have just big N equals c e to the 2t. This is a different c, so I'll call the old one c1. I can drop the absolute value and replace it with plus or minus. The plus or minus gets absorbed into the c on the other side. So then I have n equals ce to the 2t. Now we know n is 3 when t is 0, so we can say 3 equals ce to the 0. E to the 0 is 1, which tells me c equals 3. So my final equation, n equals 3e to the 2t. That's my particular solution. And it asks us to approximate the value of t when n equals 1,210. So 1,210 equals 3e to the 2t. We'll divide by 3. Let's do this on the calculator. We'll do 1210 divided by 3. Okay, so that's 403.3 repeating equals e to the 2t. Now we want to take the natural log of both sides. So that gives 5.99976 equals 2t, and then I divide by 2, and I get t equals approximately 3. T is approximately 3. Number 10, suppose that during the first year after its hatching, the weight of a duck increases at a rate proportional to its weight. The duckling weighed 2 pounds when it hatched and 3.5 pounds at age 4 months. How many pounds will the bird weigh at age 6 months? So we're going to let t be measured in months, and we're going to translate this into a differential equation. It says during the first year after its hatching, the weight of a duck increases at a rate. So the weight increases at a rate proportional to its weight. The weight is what's increasing, so that means we want the derivative of weight with respect to time. It's increasing at a rate proportional to. Proportional to means multiply by a constant. What are we multiplying by a constant? Whatever it's proportional to. And it tells us that it is proportional to its weight, which is w. So we have dw over dt equals kw. We also know that the duckling weighed 2 pounds when it hatched, so that'll be at time 0. Okay, so we have when t is 0, we have the weight is 2 pounds. So w of 0 equals 2 pounds. And then it's 3.5 pounds at age 4 months. So w of 4 equals 3.5 pounds. So we can use this information to solve for c and solve for k. We're going to separate our variables, so we divide both sides by w. We get 1 over w dw, multiply both sides by dt, so equals k dt, and then integrate both sides. So I get ln, absolute value w, we'll save the c for the other side, equals kt plus c. So hopefully you've done this type of differential equations enough time now to take a few shortcuts. We exponentiate both sides and we end up with absolute value of w, but we know that absolute value can be dropped because it's going to be absorbed into the constant term. On the right, we have e to the kt times e to the c, and e to the c just becomes a new constant. So I'm going to use my initial condition, w of 0 equals 2, to solve for c. I have 2 equals c e to the 0, which tells me that c equals 2. Okay, so w equals 2e to the kt. I'm going to use my second point to solve for k. 3.5 equals 2e to the 4k. So divide by 2. 3.5 over 2 equals e to the 4k. We're going to take the natural log of both sides. When I take the natural log of e to the 4k, I just get 4k. And then we divide by 4, and that gives me k. So ln 3.5 over 2 divided by 4, and I have k equals 0.1399. So my equation, W equals 2e to the 0.1399 t, we're asked how much will the bird weigh at age 6 months. That's when t is 6. So our weight will be 2 times e to the 0.1399 times 6. 2e to the 0.1399 times 6 is 4.63 approximately. Is this pounds? Yes, pounds. Number 11, the rate of change of the surface area of a cube S with respect to time t is directly proportional to the square root of 1/6 of the surface area. Write a differential equation to model this relationship. The rate of change of the surface area, so the derivative of the surface area, with respect to time t, so it's ds over dt, is directly proportional to, means we're multiplying by k. What is it directly proportional to? The square root of 1/6 of the surface area. So ds dt equals k times the square root of 1/6 s. And number 12, at any time t greater than or equal to 0 in days, the rate of growth of a bacterial population is given by y prime equals ky. So that's the same in our Leibniz notation as dy dt equals k times y. Y is the number of bacterial present and k is a constant. The initial population is 1,500, so we'll say y of 0 equals 1,500. And the population quadrupled during the first 2 days. T is measured in days. So y of 2, the population quadruples, so that's going to be 6,000 in 2 days. By what factor will the population have increased during the first 3 days? So let's solve our differential equations. We separate our variables. So we have 1 over y dy equals k dt. We integrate both sides. This should be looking familiar now. Natural log absolute value y equals kt plus c. And then we exponentiate both sides. We get y equals ce to the kt as our general form for this differential equation. We use our initial condition to solve for c. We get 1,500 equals c times e to the 0, so c is 1,500. So we've got y equals 1,500 e to the kt. We can use our second pair to solve for k. 6,000 equals 1,500 e to the 2k. We divide by 1,500, take the natural log, and then divide by 2. So 6,000 divide by 1,500. Then we want the natural log of that answer. Then we divide by 2. And we get k equals 0.6931. So my equation is y equals 1,500 e to the 0.6931 t. Okay, that's my particular solution. And we're asked by what factor will the population have increased during the first 3 days. So I want to know what is the population on day 3. We're going to let t equal 3. So now 1,500 times e to the 0.6931 times 3 equals, so that's our population, or we'll just say y, equals 11,998.302. Now we started out at 1,500. We want to know by what factor has the population increased. So in other words, 1,500 times what equals 11,998.302. 1,500 times what, I'll call it x, equals 11,998.302. So we take the 11,998.302, we divide it by 1,500, and we get 7.998, so by approximately a factor of 8.